Today we're going to work on power series. First of all, I want to define a power series. So, power series. The definition of a power series is that it is written, and n equals 0 is not that important, but n equals 0 to infinity of some group of terms a sub n times x to the n. Or a power series can be written like this: n equals 0 to infinity a sub n x minus c to the n. This power series is said to be centered at x equals c. So that would make a little bit different power series. Now, when you've got a power series, you've got three options. You can have a power series that converges. And it can converge for all x values. It could converge everywhere. You could have an option of a power series that diverges. Or you could have a power series that converges only for certain values. So what we're going to say is that it converges for r, where r is a radius around C, the center. So a radius around the center. Now, we talk about convergence in terms of it converging if the x minus c values end up being less than the radius. So I'm going to put that, this is in absolute values because it has to do with distance. If it's going to diverge, if something converges in this region, then it diverges when x minus c is greater than the radius of convergence. That's called radius of convergence. And then there's another piece to this when you've got a radius of convergence, and you and I must check whether it converges at the ends of this, at the ends. Now, where are the ends? They are where x minus c is equal to r. So in other words, that would be where x minus c equals r and where x minus c equals minus r. So if we've got a radius of convergence, we've got to check the endpoints. Well, the next thing we're going to do is look at an example. So the example that I want to use is this one. It has n equals 1 to infinity. And again, where it starts is not that big a deal. This has n over n plus 1. And it's got minus 2x to the n minus 1. Now, you and I can change the values anytime we want. We can start it at 0 if we'd like to do that. So let's change the limits first of all. This is not going to prove that it's convergent, but I just want to show you this. It's an algebra process. So if we want n to start at 0 rather than 1, I'm going to call this k equals 0, and I'm going to change the numerical part or the counting part to k's. So if k is 0, I know that k plus 1 is equal to n. That's the relationship. I can also say that k is equal to n minus 1. So let me go back up and put these in. I've got k equals 0, still going to go to infinity. Now on top I've got n. Well, n is k plus 1, so I've got k plus 1. The bottom has n plus 1, which is what? Well, n plus 1 would be k plus 2. And then here we'd have minus 2x. The n's don't affect x particularly. And here I've got to the k power. So you can change the starting point that way. Now, let's check for convergence. So let's check for convergence. The best process we use here is the ratio test. So you will use the ratio test like all the time, basically, when you do these. So let's check using the ratio test. What I want to do is I want to take the limit, and I'm going to use k here as k approaches infinity. I'm going to put this in here. Remember, the ratio test takes the next term, okay? So k plus 1, the next term is k plus 2. K plus 2, the next term is k plus 3. Then I'm going to put minus 2x to the next term, which is k plus 1. I'm going to divide that by the original. So this one has k plus 1 over k plus 2 minus 2x to the k. I need to put absolute values, and I need to force that to be less than 1. Now, I want this to be less than 1 because I want to find out where it converges, and I can do that with this process. So I've got a complex fraction. I need to set it up so that I can solve it or find the limit. So let's take the limit. This is the limit as k approaches infinity. I'm going to take the reciprocal of this one and put it next to it. So let me write k plus 2 over k plus 3, and then this minus 2x to the k plus 1 was in the numerator. And then this is multiplied by the reciprocal of this one, which is k plus 2 over k plus 1. And this was in the numerator of this fraction, so it's in the denominator of this one. Okay, so just k. And that stuff's got to be less than 1. So now I have to do some limit work. Well, you'll notice you've got k plus 2 times k plus 2. So I've got to take the limit as k goes to infinity of k plus 2 squared over k plus 3 times k plus 1. And then I've got these. Well, they're almost identical, except this has an extra power, so I'm just going to do this. I'm going to put minus 2x. Algebra tells us that we subtract exponents, so k plus 1 minus k is 1. So there it is. And this stuff's got to be less than 1. Well, you can use L'Hopital's rule. You can use all kinds of work to do the limit here. You're going to have k squared plus 4k plus 4. Here you're going to have k squared plus 4k plus 3. That limit of this fraction right here is going to be 1. Now, I didn't do the work, but you can figure that out with, like I said, L'Hopital's rule or some other version. So that goes to 1. And so what we end up with is, that's the only part with k. So the limit has actually been taken, and what we end up with here is this. Minus 2x in absolute values is less than 1. Well, that's not terrible to solve, although you haven't had to do that a lot since algebra. So you take minus 1 is less than minus 2x is less than 1. Divide through by minus 2 on all three parts. When you divide by minus 2, it swaps this around. So we end up with this. We end up with 1/2 is greater than x is greater than minus 1/2. So that's our interval of convergence. Now we've got a little bit more to do with this because we have got to find what happens at the endpoints. So let's try to deal with that. Let me move this down a little bit. Okay, so let's check 1/2. So check 1/2. Check x equals 1/2. So I come back up here to my problem, and I put 1/2 in for x. So here is what I've got. Now let me do it with this one because I used k. Not that it's a big deal, but we've got this and this. We've got k plus 1 over k plus 2, so k plus 1 over k plus 2. And then we've got 1/2, so minus 2 times 1/2. That is minus 1, and then we've got to the k. So that is a series that goes plus 1 minus 1 plus 1, okay, alternating series. And the terms are basically 1s. Now I know that's not exactly 1, but it's got a limit of 1, so the terms go to 1 here, and this is alternating. You might recall that if a series has terms that do not go to 0, then it automatically diverges. So this diverges, so this is not part of our interval of convergence. Now we've got to check the other piece. So let's check x equals minus 1/2. Put that in. We've got this. We've got k equals 0 to infinity, k plus 1 over k plus 2. We've got minus 1/2 times minus 2, so that's just 1 to the n. Well, this one doesn't even alternate. It is just essentially adding 1 to itself an infinite number of times. That one diverges. So we've got two outcomes here. We've got the interval of convergence. So our interval of convergence is minus 1/2. I'm going to start with the smaller one, to plus 1/2. You have to write intervals with smaller to larger. So minus 1/2 to plus 1/2. And we've got to figure out some other things, like what's the radius of convergence? Well, if this is the interval, cut it in half, because that's a diameter essentially. So the radius of convergence is equal to 1/2. And you'll notice that x didn't have anything subtracted or added to it, so the center is at 0. So this particular series that we had up here converged for any x value between minus 1/2